Bismillah. So today we're going to be talking about RAAS, or the Renin-Angiotensin-Aldosterone System. Now this is a part of renal physiology and is something that's most frequently taught in preclinical medicine, for example years 1 and years 2. So what even is RAAS? So RAAS essentially is we're going to be talking about an emergency system. Why do we need this? So in your body you have the different organs, and these organs need to be maintaining their normal blood perfusion, meaning essentially they need their normal blood supply. So what happens when it goes wrong? For example, you have low blood pressure or low blood volume. That is when your emergency system comes into play, which is, in this scenario, RAAS. So what this emergency system would do is it would then make adjustments, which we'll talk about now, and the way in which it goes about it. And the end goal is that it is going to be trying to increase your blood pressure, as well as increasing your blood volume and preserving your water and sodium levels as well inside the body. So where do we start? Let's break it down. Firstly, renin. So essentially we're talking about renin, angiotensin and aldosterone in that order. So we're starting off with renin. Where is renin released? We're looking at the kidney. This is going to be step one. We're looking straight at the kidney. Now, in terms of the kidney, we're now going to be zooming a bit more further into the nephron. This is something you most commonly came across at A level. However, you may not have come across it looking like this. It may have been a bit more spread out, quite wide, with the glomerulus facing the other way or something like this. That's the most frequent types of diagrams that come across in an A-level textbook. However, we're slightly adjusting this as we're adding a bit more information. So just to label, here we have your glomerulus here. This then leads into your proximal convoluted tubule, so I'll just label this. So you have your glomerulus here. You have your that's your Bowman's capsule. Inside it is the content of that is the glomerulus. Then you have your proximal convoluted tubule, which essentially is here, which then leads to your descending limb of your loop appendale, and then your ascending limb of the loop appendale. Then we have the distal convoluted tubule, which is here, and that finally leads to the collecting duct. Now for when we're covering the renin-angiotensin-aldosterone system, we're most commonly going to be focusing a bit more at the glomerulus to the DCT, this junction here. What do we call that? We call this the juxtaglomerular apparatus. So I'll write that here. The juxtaglomerular apparatus, also known as the JGA. So what is this consisting of? We're talking about the glomerulus here, and as we look at the glomerulus and we look at the blood inside here, let's talk a bit more about this. Let's label this. So here we have your afferent arteriole. So I'll also write that down here. I'll just write afferent arteriole, afferent art. So afferent arteriole, A for arriving. It's arriving into the glomerulus. Here what you have then, it follows all the way through. Then you get your efferent arteriole. So your efferent arteriole, the E for exiting. So your efferent arteriole. We'll come back to this later on and discuss a bit more about this, okay? So now let's look a bit more further before we move on. Your afferent arteriole, in the walls of your afferent arteriole, you have a specific type of cell. So this is going to be called your JG cell, also known as your juxtaglomerular cell. So I'll just draw here. Now these cells here, these are going to be where you release renin from. So that is your JG cells, also known as your juxtaglomerular cells. Now, in your DCT, you have a different type of cell. These are called your macular denser cells. So I'll just draw a few cells here. This is in your DCT. However, these cells are your macular denser cells. So your juxtaglomerular cells, these are essentially baroreceptors. They're going to be detecting any change in your blood pressure. However, your macular denser cells, these are chemoreceptors. They're focusing more on sodium concentrations throughout around this region, okay? So now, like we said, we're starting off with renin. We mentioned that renin is released from your juxtaglomerular cells, which are lining your afferent arteriole. So I'll also write here JG cells. So JG cells. And this is very important, so make a note of this. because this is where renin is released. But what triggers the release of renin? So we discussed here, so your juxtaglomerular cells, these are also baroreceptors. They're inside the walls of your afferent arteriole. What does this mean? They detect blood pressure. So let's say, for example, you have your afferent arteriole. It's arriving into the glomerulus. Now, the more blood pressure there is, it's going to cause the arteriole to stretch more and more. And the juxtaglomerular cells are going to be detecting the stretch. So for example, if you have decreased blood pressure, that's going to be causing decreased stretch. What does that mean? That is then going to cause the release of renin, which will then cause this cascade to happen, as we'll talk about shortly. Now, the other way you can trigger this is you can trigger this by having decreased sodium at your macula densa. As it detects decreased sodium, it now essentially just thinks that there's not enough blood being filtered. What does that mean? It's then going to signal to the juxtaglomerular cells to release renin, again triggering the cascade. Now the final way is going to be via sympathetic nervous system activation, your fight or flight. So for example, a person is dehydrated, or they're in shock, or it's like maybe something along this nature, or just a normal or a stress response. Something like this would then potentially cause sympathetic nervous system activation. What is that then going to cause? The release of noradrenaline, also known as norepinephrine. Now, this is then going to be binding to the beta-1 receptor on the juxtaglomerular cells. This is then going to be triggering the release of more renin, or increasing the release of renin inside the blood. So we've now established that through the kidney, specifically the juxtaglomerular cells, through a variety of different ways. Remember the three ways. Firstly, as the JG cells, the juxtaglomerular cells, they're baroreceptors. They're detecting the reduced stretch, causing release of renin. Or by the macula densa, they detect decreased sodium, hence causing the signal to be sent to the juxtaglomerular cells, thus releasing more renin. Final thing, like we said, just to conclude, sympathetic nervous system activation, increased activation of the innervation of the sympathetic nervous system, will eventually cause a binding to beta-1 receptors via noradrenaline or norepinephrine, hence causing the release of renin. So we've established renin has now been released into the blood supply, or there has been increased release of renin into the blood supply. So great. So from the kidney, we're now getting renin. So this is now inside the blood, or the supply of renin is now increased inside the blood. So now let's start looking at somewhere else. Let's look a bit more at the liver. So at the liver, we're going to be focusing on something called angiotensinogen. But let's stop there. So the name is the renin-angiotensin, not angiotensinogen. So let's break down angiotensinogen, the word. So angiotensin. You can break this down into three parts. Angio, we're talking about blood vessels. Tensin, we're talking about blood pressure. OGEN, we're essentially just saying this is inactive. It's always very useful at times to break down the word just so you can understand it a bit more. So this is not our final product. It's just the inactive version. This is going to be being produced from the liver, and there is a quite consistent level of this throughout the blood. However, it is waiting to become activated. How does it become activated? So you have your angiotensinogen from your liver, angiotensinogen, and this is going to be forming, like we said, this is inactive. It ends with OGEN. It's inactive. And it's important to know that your renin is an enzyme. It's a protease enzyme. It's going to be breaking this down, removing this, the OGEN essentially, and it's going to be converting this to form your angiotensin 1. Angiotensin 1. Okay, now we've got angiotensin 1. So, angiotensin 1, you think to yourself, okay, great, surely that's all done. However, angiotensin 1 is still a bit of a precursor. It does have mild vasoconstrictory effects. However, there isn't really much clinical relevance to this. However, what we're then going to form from this is we're going to form angiotensin 2. But we can't have, or how do we essentially form angiotensin 2? Let's now look at step 3. Let's look at the lungs. The lungs are going to produce an enzyme called ACE, angiotensin converting enzyme. So I'm just going to write here ACE, or you can just write angiotensin converting enzyme. And that's going to allow for your conversion of your angiotensin 1 to your angiotensin 2. And this here is what we want. Angiotensin 2 is going to be having the big impacts, okay, or the big effect. And there's four main effects you need to know. So, firstly, the first effect going to be angiotensin 2 generally has a vasoconstrictory effect. What does that mean? It means that the blood pressure is going to increase as you're vasoconstricting. You're tightening the blood vessels, okay? That's the first one. So write that down. It has a general vaso C effect, okay? Great. Number 2. The second effect it has, let's look back at your efferent arteriole. I said we'll come back to this in a second. So your efferent arteriole is surrounded by essentially a lot of smooth muscle. Your afferent arteriole, your angiotensin 2 is going to work on your efferent arteriole and it's going to cause a vasoconstriction. Now what does that mean? Let's think here. So your blood is going here through your afferent arteriole into your glomerulus and it's trying to leave. Now, as it's trying to leave, if we're vasoconstricting it, if you look here, we're vasoconstricting, we're tightening it, it can't get out now. So what that means is the blood is essentially going to be pushed back into your glomerulus, and what effect is that going to have? Is it's going to increase your GFR as well. So your angiotensin 2, another effect it has is that it works on your efferent arteriole, and it's having a vasoconstrictory effect. What does that mean? Like we said, blood backs up. Is this going to be causing an increase in GFR? And what that means is a glomerular filtrate rate, okay? Another thing you should also note here is that it is also going to be causing increased sodium reabsorption as well. Why is this relevant? Now, with sodium reabsorption, I want you to remember, where sodium goes, water follows. So, if sodium is reabsorbed back into the blood, what is that going to mean? That's going to mean water follows into the blood as well. That means that we're going to be increasing our blood volume. Now remember our core problem. Our problem was that there was low blood pressure or low blood volume. So we're now combating that. As sodium is entering the blood, water is following, we're increasing your blood volume, okay? Great. So the third thing to look at now, we're now going to be focusing on the third part of this. So we said renin, great, we've covered renin. We covered renin release and so forth. We've covered angiotensin as well. Now we're going to be covering the last part, the aldosterone aspect. So what does angiotensin 2 do? The other effect it has is that it goes, and on top of your kidney, you have, I'll just draw here, essentially, it looks a bit like this. This is going to be your adrenal gland, okay? So angiotensin 2 is going to be working on the adrenal gland, specifically the adrenal cortex, to release aldosterone. What is the effect of aldosterone? It has a few different effects, but let's focus on one specific one. Again, it's going to be causing increased sodium reabsorption. Let's cover it again. What does sodium reabsorption do? That means where sodium goes, water follows. So if sodium is getting reabsorbed into the blood, that means water is going to follow it. Again, we're combating the problem, increasing your blood volume. Great. Now, the third step is going to be your angiotensin 2, causing your increased aldosterone, and that is going to cause your increased sodium reabsorption. All right, reabsorb. Sorry, no, let's just write that one. Okay. So increased sodium reabsorption. Fourth step, one of the final effects of angiotensin 2 is it's going to be going up to the brain and it's going to be working on the posterior pituitary. So remember, the pituitary gland, it's below the hypothalamus in the brain, and the posterior pituitary releases your two main hormones. Try and remember what they are. I'll give you a second. They are oxytocin as well as ADH. ADH stands for your antidiuretic hormone. So what does that mean? Normally, diuresis, we're saying urination. So water is leaving the body. What does antidiuretic hormone mean? We're stopping urination, or we're trying to reduce it. Why is that relevant? Because let's think again. What was the problem originally? It was that we have got decreased blood pressure or decreased blood volume. So if we have urination, that is going to be further decreasing blood volume. We're essentially removing the water from the body. What happens if we use ADH or increase ADH, antidiuretic hormone? That means less water is going to be leaving the body. Perfect. More water is inside the blood. We've got a higher blood volume, or we're maintaining that blood volume. Okay. So that is, I'll write here, I'll write ADH as a final one. It can be causing increased ADH release. So that is essentially the renin-angiotensin-aldosterone system, also known as RAAS. However, is that all you need to know? No, there is actually more you need to know. However, I will cover this, God willing, in future videos. There's also the clinical relevance as well. Now, in cardiology pharmacology, we're going to be talking a bit more about things such as your ACE inhibitors, your angiotensin receptor blockers, and you can see behind me, ACE right here, angiotensin we discussed. So cardiology pharmacology is a huge clinical relevance of this system as well as inherently the system itself. It's there, it has a clinical relevance to try to combat low blood pressure as well as low blood volume. So that concludes this video. If you found it useful, please subscribe to the channel as well. We're, God willing, going to be uploading quite a few different videos over the next period of time, however long that is. And I hope you found this beneficial.